Okay, so on to the rest of the lesson. So, we were talking about this strong force. It needs to come from somewhere. In order for you to do anything, in order for you to push something across a room, you have to put energy into it, right? Every force has to have some energy involved in it, yes? Kinetic potential, something going on, okay? So this force needs to get its energy from somewhere. Where does that energy come from? That energy comes from this. This mass that's missing isn't actually missing. What happened is I take this mass and I convert it into energy. I convert it into what we call nuclear binding energy. Okay? Now, how do I do that? I do that very simply. I have this much missing mass. I can figure out exactly how much energy I have by doing what? Well, I could do E equals mc squared, convert that to kilograms, multiply it out. But the easier thing to do, since I am talking about a nucleus, is to go, well, I know 1U equals how many mega electron volts? So how much binding energy do I have? Well, I have 0.0304 missing mass. Convert that to mega electron volts. How? Multiply. What do you get? What do you get? What do you get, ladies and gentlemen? Yes, ma'am. Because if you had one U, that's 931, right? If I had two U's, how would you figure out how many electron volts you have?
No, I mean, I know how we're converting it. Why is like the missing? Because I know the missing that.
So because effectively what we're doing is we're cutting out having to do all the math in here. So what we would have to do is we would have to convert this mass, right, into kilograms. You convert it into kilograms by multiplying that by 1.66 times 10 to the negative 27, yes? We could then plug that answer we get into this formula and figure out how many joules of energy we have. But since we're already talking about a nucleus and an atom, we would eventually have to go back down to mega electron volts anyway. So we're cutting out all those middle steps and just multiplying the missing mass in U's by the conversion factor of 931 mega electron volts per U. Does that make sense? No problem. I'd rather you ask the question. Okay, so what do you get?
I got 28.3.
Perfect. So your binding energy comes out to 28.3 mega electron volts. Make sense? Now that's the total amount of binding energy in the whole thing, okay? With binding energy, there's lots of different things you can do. One of the things that you can do with binding energy is you can figure out how much binding energy there is per nucleon, okay? To figure out the amount of binding energy per nucleon, so per nucleon, remember, we're talking about per particle in the nucleus. You would take that number and you divide it by the number of nucleons. So it's binding energy divided by number of nucleons. So in this case, for helium, you do 28.3 mega electron volts divided by how many nucleons do we have? 4. Make sense? Yes, no, maybe, sometimes, on answers there. Okay? Does that make sense? Yes? Do you want to do a little practice so you know what you're doing? No. Yes? Okay, let me upload this.
Wait, what does that give you?
What would 28.3 divided by 4? What does it give you, answer-wise?
0.78.
28.3 divided by 4?
7.08.
I think it's 0.7. 7.08 mega electron volts per nucleon. Does that make sense? Okay, so let's see if this. Hold on. Stupid thing will not load. Okay, so what I'm going to give you now is a fun-filled chart. Okay? If we look at your screen, right? Hold on, let's see.
Do you want us to stop it, Mr. G?
Yeah, hold on. I'm trying to get this thing to work. There we go. Should have worked. Did it upload for you guys? Where did it upload? Ah, there it goes. Come on, post. This should pop up in a second. There we go. Okay, so if you open up this chart, okay? Doesn't have to do that. Okay, so here you have the most stable isotopes of all the elements of the periodic table as the composition being created. Okay? No, I'm not going to make you do them all. Okay? Now, Let's pick an interesting one.
Radium.
Let's do iron. Everybody find iron. Okay? And find the most common form of iron. Okay? Does everybody see that one? So if we're looking. Okay? So you're looking at iron 56. Does everybody see that one? Okay. So, what I want you to do is I want you to find, okay? So, calculate. I want you to find the mass of iron 56 based on its nucleus. Then I want you to find the mass deficit and find the binding energy and find the binding energy per nucleus. I give you 5 minutes. Go. Just do the same thing we just did. Salud.
Is the internet working?
It is for me. Guys, can you see me at home?
Yeah, we could see you.
Yeah, okay. Going on over there?
My board, I just get buffering on the smart board.
Last time I had to completely turn the board off and then turn it back on.
Well, I did that, it's still doing it.
Oh, Peter, he'll come down and fix it real quick. Oh, I'll watch it for a second while you talk. There's the board. Do you want to go?
Yeah. hold on.
Almost have the next step now. But then single volt of energy. No. There's 30, 26, and then it's 55, 56. 26 plus 30 is 50.
You finished?
What? For what? What's the first one?
Sophia, you done?
How do you get 9? I'm doing it in U. What do you do? Kilograms? It's in U. It's 1.0073 U per proton.
Do we need help? We want to work on the beginning part together? Okay. So we have to calculate the mass of Fe based on its nucleons. Well, if we look, okay, Fe, 56. What's the atomic number of iron, ladies and gentlemen? I called him, I left him a message, he wasn't in his office.
Okay, so I don't have a student Wi-Fi. Do you guys have student Wi-Fi?
You're welcome to work, so maybe you're, so the kids at home, can they see you still?
It's close enough.
The kids at home, yes, they can see me, but the kids there, the student Wi-Fi is not working.
See if one of them can jump on one of their hotspots and piggyback off of it. Okay, so atomic number is 26, right? The atomic weight, or the universal mass units, is 56, yes? So, how many protons do we have? How many neutrons do we have? How many protons?
26.
26. The atomic number tells you the number of protons. How many neutrons do we have?
30.
30. You do atomic weight minus atomic number. That gives you that. Correct? Good? Yes?
Yes, again, minus 30.
Yes? Okay.
They're not going to have 37 decimal places.
So when you do that, right, you're then going to take these values and multiply them by the masses of a proton that you have and the masses of a neutron that you have. Get that answer and add it together, and you should get the mass of the nucleus, what it should be. So you do 26 times 1.0073, right? And 30 times 1.0087. What do you get for the total mass of protons? What do you get? What's 26 times 1.0073?
26.1898.
26.1898.
1898.
And what do you get for the mass of neutrons? So 30 times 1.0087. What do you get?
30.261.
30.261.
261.
Even? That's it? Does everybody understand that? Does everybody agree with those two numbers? Did everybody get those two numbers? Now, what do you do with those two numbers? Add, right? So 26.1898 plus 30.2610. What do you get? 56 point.
So close.
Yes? According to the chart that I gave you, what is the actual weight?
55.93.
Say it again, Tim. 55.
55.935.
935.
Do you want one more rest?
Give me whatever it says.
Oh, so that's 9349.
9349. No. Okay? We have the calculated, we have the actual. Okay? So we've calculated the mass based on its nuclei. So now we need to find the mass deficit. How do we find the mass deficit? Subtract this one from that one. What do you get?
I got 551.588.
Your mass deficit came out to 0.51.
58.
Does everybody agree? Yes? That's your mass deficit. Now you need to find the binding energy. How do you find the binding energy? Multiply that by 931. What do you get?
Should I give you all the decimals?
Yeah, give it to me. 480 point.
263,798.
Units? Okay, and then find the binding energy per nucleon. What do you do?
Divide by 56.
Divide that by 56. What do you get? What do you get?
8.5761. Not the whole thing.
8 point, no, so 8.5 what?
8.5761.
So we'll say 8.58, right? Yes? Mega electron volts per nucleus. Does that make sense? Okay, can you do one without me leading you, hand-holding you all the way through?
I got so close.
Okay? Alright, let's pick everybody's favorite. Let's pick the fuel for little boy. What was the fuel for little boy?
Uranium 235.
Go! Uranium 235. Okay? The atomic number of uranium is?
92.
92. So do this same process.
Yes, okay. I'm gonna do the brown square one now. You can come around as well.
You're getting homework on this tonight.
I got darn close using mechanical the last one.
What do you get?
8.6.
Round.
Darn close. Well, because I have to read a physical gauge, so I can't get 37 decimal points. Are they good? Okay.
Don't think I'm crazy.
What? The whole thing? Basic count. The last one.
You get the answer? What do you get?
For the mass, I got 236.9157.
Mr. G,
Yes, hold on. What's up?
do we have a quiz tomorrow?
Yes, you do.
Oh, okay. All right.
So, Francesca, what do you ultimately get for the binding energy all the way at the end?
1,742.
Okay. And per nucleon?
7.4.
It's about 7.5 practically, but yeah, you're good. Make sense? Yes? Cool. So I just gave you homework. Okay? Your homework is to do the same thing with elements 2 through 11. And you can show me the work. You will have one of these on your quiz tomorrow. The homework is up on your Google Classroom. You can get it started now. Those of you that are home, you can get it started now and you can peace out from the meet. I'll see you guys tomorrow.
Have a nice day.
Be good, guys.